Okay, so for the first part of the Unit 2-3 notes, we'll pick up here with projectile motion. So again, a lot of this stuff is going to be like projectile motion, which we dealt with last year, where we had two-dimensional motion. We will add in, though, a few more systems of equations type problems, and then obviously a few questions where we have to do derivatives and such to help us out as well. But anyway, just summarizing, right, so take a minute to write this down as you need to, or to fill in any other information, I guess, on the example page. But anyway, projectile is an object moves in two dimensions under only the influence of gravity. So the key here is when we hear projectile motion, that actually is telling us that there's no air resistance, because the only force, the only acceleration acting on it is that of gravity. So again, the free fall acceleration, which we know is 9.8, is constant during the entire motion and always directed downward, and the effects of air resistance are considered negligible unless for some reason they tell us otherwise. So then I throw in down here, I say the trajectory, the path of the projectile, it is always a parabola for a projectile motion. Why? So let's think about why. Why is this motion always going to be a nice parabola? Well, first of all, right, if I think about the vertical displacement, right, if I think about the vertical displacement, it makes a little bit of sense that it's going to follow a parabolic motion, because vertically speaking, we know we're using the equation v sub 0t plus 1/2 at squared, which is a quadratic function, right? And so because of that, its vertical position is going to mirror that of a parabola. The other reason, though, that it's a nice symmetric parabola is because, again, there's no air resistance. And if there's no air resistance, we know it's moving constantly to the horizontal direction, right? And if it's got a constant horizontal velocity, then as it goes up and down, right, it's going to continue to space out evenly as it goes. So that's how I know that, in fact, it is going to have this nice symmetry involved. Now again, in real life situations, the kick or throw or whatever we're looking at here would actually follow kind of an oblong parabola. And what I mean by that is the first half of it would actually be a little bit further, and then the second half would actually be a little bit steeper. So this first half of the motion would actually cover a little bit more distance, and the second half of the motion would tail downward a little bit quicker. And that's just because the air resistance would compile up, and we'll deal with that a little bit more later in the year. Right, but make sure you're comfortable with the basics of projectile motion. The big thing from that first slide is remembering that when you see the term projectile, it means there's no air resistance and only acceleration due to gravity. So I threw in remembering, right, the horizontal and vertical components. They're completely independent of one another, with the one exception, right, that one exception being time. Right, going through, we did all the equations last year where we would do, right, for the horizontal displacement, the only equation I need is v equals delta x over t, and that's because, right, the horizontal motion is constant. For the vertical motion, I can use any of my kinematics equations, right? So I could use my VOTAD, I could use my v squareds, all of those apply to my vertical motion here. Okay, so I'm using any of those. The one element that ties those two together is time, right? That's the only thing that I can actually use to then combine these two equations together. So make sure you're comfortable with the basics of that. Again, just refreshing as we go through this section on those key relations. So then the first couple examples are actually just really review questions from last year, making sure we still remember the basics of projectile motion. So the first one here, stuntman drives a car off a 10-meter high cliff at a speed of 20 meters per second. Well, when he's initially going off the cliff, I know that he's moving at a horizontal velocity of 20 meters per second. It does not give me any type of incline or angle there, so I'm going to assume that's perfectly horizontal as he leaves the cliff. And then I'm looking for how far does he go, so what's the delta x, right? What's the horizontal displacement that he lands away from the cliff? So if I'm looking for delta x, the first thought I should be working with here is, right, v equals x over t. I know my horizontal velocity. The problem is I don't know the time, at least not yet. Right, but again, this is a pretty easy question to solve, hopefully, right? Just go to my vertical measurements. I know my initial vertical velocity is 0 because he's not moving up or down. My acceleration due to gravity is 9.8. My height of the cliff there, my delta y, if you will, is 10 meters. And so since I have those three measurements, I can pretty easily find my time. Right, so delta y equals v sub 0t plus 1/2 at squared. And then solving for my time, right, I just get 10 equals 1/2 9.8 times t squared, and then solve for that. So when I solve for that time, I get that to be about 1.43 seconds. And then again, that tells me how long it takes before the car hits the ground, right? Regardless of whether it falls straight down or whether it's going off to the side, it's going to take exactly 1.43 seconds for it to fall downward 10 meters with that acceleration, right? So again, no matter how far it goes, it's going to take that long for it to fall 10 meters down. So since I now know the time, and I have my horizontal velocity, it's easy enough to bring this all together. So 20 equals delta x over t, so over 1.43. And in solving for delta x, we can just multiply the two together. And of course, you can then use your 20 rule, right? Just 2 times the 10 rule. So what does that end up being? 28.6 meters, right? So that's how far from the cliff the car ends up going. Again, hopefully a pretty basic review question for us. Okay. Question 2, a little bit more involved here, but it's still a review question. It just has different legs of motion, if you will. Get it because it's a frog. He's jumping. Legs. Never mind. Okay, that was pretty bad. But anyway, high-speed camera shows that a frog can crouch and go and rapidly extending its legs 15 centimeters during a 42 millisecond push-off. Okay, so for the frog, as the frog is accelerating away from the ground, so again, the frog is pushing off, he's accelerating, and then he's going to leave the ground with a certain velocity. So my goal for this projectile problem is I want to find that velocity at which he leaves the ground with, right? So if I start thinking through the information, well, I know the 0.15 meters is how far he accelerates. He does so for a time of 42 milliseconds, which is 0.042 seconds. And then he starts at rest, right? We're assuming that he's jumping off the ground, so he's starting at an initial velocity of 0. So if I use these measurements, I can find my acceleration and then my final velocity. Or, if you remember this equation, and maybe not because we don't use it very often, but because it's a constant acceleration, or we'll assume it's a constant acceleration, you could actually use this equation, which is really just taking my average velocity times time. But the reason I'm doing that is I'm looking for my final velocity, and I know the other measurements, right? So either use two equations using kinematics, or I could just use this one to find my final velocity. It truly does not matter which one I choose to do. When I solve for that final velocity, though, I should get something to be pretty close to about 7.14 meters per second. Okay, so this tells me how fast the frog is leaving at that 30-degree angle. Okay, so the frog is leaving at 7.14 meters per second, again at that 30 degrees above the x-axis. Okay, so I've got that information to work with. Now that I've got this information, this is where it's a pretty standard projectile problem. Right, part A asks me how far he goes, and that's speaking the horizontal displacement there. And then part B, what's his maximum height. Right, so for part A, if I want to find out his displacement, his horizontal displacement, I need to know his horizontal velocity, which is easy enough, just 7.14 times cosine of 30, which in this case would be, that comes out to be about 6.18 meters per second. So I've got that information. The other thing I have to find is the time, right? How long is he in flight? Well, I know he's going to go up and then back down. So there's a couple ways that I could approach finding the time. One way would be using my vertical measurements. I know his initial velocity is 7.14 times sine of 30, which is exactly then 1/2 of 7.14, so 3.57 meters per second. I know that the acceleration due to gravity would be a negative 9.80. I'm defining it as negative since I've defined this as a positive meters per second squared. And then the key here is you could break it up at one of two places. You could either break it up at the top of the path, where we know that the final velocity would be 0, or I could actually break it up at the very end of the path, right, where the final velocity over there would be negative 3.57 meters per second. Because I know that the vertical velocity when he reaches the same height is going to be the same magnitude, but it's going to be the opposite direction. It doesn't matter which of these I use, so I'm just going to use my VOTAT, right, my velocity as a function of time. So I'm going to set up this equation here, and then I'm going to solve for the time. Now, if I use 0, I need to make sure I end up doubling the time. The one benefit of using the negative 3.57, if I choose to use the negative 3.57, then I don't have to double the time because I'm actually already finding the time for the total flight. Okay, so if I do choose to set it up this way, I actually find the time directly to be about 0.729, so about 0.73 seconds. Again, if you used 0, you would find a time that's about half of that and simply need to double it. Right? So anyway, finding the time, hopefully not a bad process. Just define your final velocity at either the top or at the end of the path. But anyway, I've got the time. And now that I have the time, finding delta x, just like our last problem, just like example 1, is pretty easy to do. I'm going to take my horizontal velocity, 6.18 times the time, so 0.729, and that tells me that he jumps about 4.50 meters horizontally. So I've got the horizontal displacement. Now, one of the biggest mistakes that you have to watch out for, I know this got a lot of us the first time or two through last year. Just because we know that he goes a distance of 4.5 meters horizontally does not mean we can try to break this up into a right triangle. I don't want to, for instance, cut that in half and call this 2.25 and this 30, right? Think about why we cannot do this, right? We can't do this because we know that it's not a linear motion for the vertical measurement. As the frog jumps vertically, he doesn't follow a straight line but falls. So he's not going to reach that same height as if he was jumping at 30 degrees. Again, pause for a second, make sure you're comfortable with that, because that's actually a very, very big understanding, right? And it's something that I know tripped a few of us up last year, right? The frog will not reach the same height as if he was just jumping in that straight line because he's curving downwards thanks to acceleration, right? So the only way that I can find for part B, the only way that I can find his maximum height is, again, easy enough. I just come to my vertical measurements. So I know my initial vertical velocity is 3.57, I know the acceleration is negative 9.80, and I know his final velocity at the highest point is 0, or I could just use the fact that the time to reach the highest point would be half of that 0.729. You could do either of those approaches. I'm just going to go ahead and do this one and then do my velocity squared function. So setting this up, I know all of the measurements except delta x, or in this case I'll call it delta y, since it's my height, right? So again, 0, 3.57 squared, minus 19.6, 2 times 9.8, and then delta y. So then when I solve for delta y, I get that to be about 0.650 meters high. Okay, so again, however you're comfortable solving for that, hopefully you got an answer that's pretty close to this. I do want to make sure you are watching out for the fact that it is not going to come from this right triangle, right? We cannot do that because it does not follow linear motion for the vertical displacement. So make sure you're comfortable with that. And just to reiterate that point a little bit more, let's go through this example. So pause it if you need to read this one, right? But in this case, you're shooting at a coconut in a tree. So you've got your tree and then you've got the coconut about to fall from the tree, and you want to know, am I aiming at the coconut, am I aiming above it or below it? So I'm standing down here. Am I taking aim directly at it, directly above it, or directly beneath it? Now, we saw a question like this when we looked at the hunter and the monkey, where they were at the same height last year. And most everybody agreed that for the hunter and the monkey last year, you'd aim straight at the monkey because as the bullet fires, the bullet falls, and so too does the monkey. And in this case, what we're actually going to find is the same is still true. Now, it plays a little bit against your intuition, right? Because you're thinking, if I fire the bullet upward, right, and the monkey begins to fall, I don't want to aim at where it is because the bullet's going so fast, it's going to miss the monkey if it just stays on that straight line. But keep in mind, what is the bullet actually doing over time? Well, if I was setting up a function for the bullet's vertical motion, right, if I was looking for the bullet's height, I would set up this function, v0t plus 1/2 at squared. This would represent where the bullet was if there was no acceleration due to gravity, and that would represent then its height as if it was traveling along a straight line. So its height would just be continuing to get higher and higher. However, the bullet is accelerating downward, right? We know that this would be a negative 1/2 times 9.8, and that should have been t squared, by the way, but t squared. This part right here tells me how far the bullet will fall. This tells me the change in y that the bullet falls due to gravity. Well, if I consider the monkey, as the monkey releases, or as the coconut, I should say, it's not a monkey in this problem, but as the coconut releases, I know it's got the exact same change in displacement for the y component, right? Again, if I was setting this up, it'd be 1/2 at squared because its initial velocity is 0. But that tells me then it's falling at that exact same rate. And so because of that, both the bullet and the monkey will have fallen the same amount by the time that the bullet reaches that horizontal displacement. So we actually do still aim directly at the coconut.